Good morning, students. Today we are going to see Cole's law of independent migration of ions. According to Cole's law, the equivalent conductance of any electrolyte at infinite dilution is the sum of equivalent conductance of cation and anion at infinite dilution. Mathematically, it can be represented as lambda infinity is equal to lambda c plus lambda a, or lambda positive plus lambda negative, where lambda infinity is equivalence conductance of electrolyte at infinite dilution, lambda c is equivalent conductance of cation at infinite dilution, and lambda a is equivalent conductance of anion at infinite dilution. Now, just see this table. In this table, this is the pair of strong electrolyte in which Cl atom is common. In this case, bromine atom is common in this pair. In this pair, NO3 is common. So, and also see, it is the potassium chloride, it is sodium chloride. While in this case, it is potassium bromide, it is sodium bromide. So, lambda infinity, that is equivalence conductance at infinite dilution, for KCl value is 149.86. For NaCl, its value is 126.45, and the difference between these two value is 23.41. Again, for this pair, this difference comes same, though the value is different. Equivalence conductance of KBr, it is 151.92. This value is different from your equivalent conductance of KCl. And that of NABr, equivalence conductance of NABr is 128.52. So, in both the case, difference is constant. In this case also, the difference is constant. That is, if you subtract 126.45 from this value, it comes 23.41. In this case also it is 23.41. In this case also it is 23.41. Now, just see, and this column, in this column we see that potassium ion is constant here, it is same here. So, in this case, the difference is 2.06. Now, just see here, sodium ion is common in this pair of electrolyte. Difference is 2.06. In this case, lithium ion is common and difference is 2.06. And it is very interesting. So, on the basis of above observation, Cole's conducted that each ion makes, it is important, a definite contribution to the total conductance of electrolyte at infinite dilution, which is independent of the other ion present. Now, we are going to see application of Cole's law. First application is calculation of equivalence conductance at infinite dilution of weak electrolyte. So, it has been stated earlier that the equivalence conductance goes on increasing on dilution. This increase is almost linear with respect to under root of delta C in a case of strong electrolyte. So, the equivalence conductance at infinite dilution can be obtained by extrapolation of the graph. But in case of weak electrolyte, The increase is not linear and it cannot be determined by extrapolation method. So, it is indirectly obtained from Kohlrausch law. So, equivalence conductance value at infinite dilution of weak electrolyte is indirectly obtained by using your Kohlrausch law. It can be done by two ways. First, from your transport number method. So, for this, two strong electrolytes containing cation anions of the weak electrolytes are taken and their equivalence conductance at infinite dilution, that is lambda infinity, are determined by extrapolation. For example, in order to calculate lambda infinity of weak electrolyte ammonium hydroxide is weak electrolyte. Thus, two strong electrolyte, that is ammonium chloride and NaOH, are selected. Lambda infinity value for these electrolytes are determined. First, the equivalence conductance of cations and anions are given by lambda NH4 plus is equal to lambda infinity ammonium chloride multiplied by transport number of ammonium ion. Lambda OH minus is equal to lambda infinity for NaOH multiplied by transport number of OH minus. From Kohlrausch law, we can write lambda infinity is equal to, for ammonium hydroxide, it is equal to lambda NH4 plus lambda OH minus. Hence, lambda infinity for ammonium hydroxide can be calculated. Second method is 3 electrolyte method. In this method, 3 electrolytes are selected which on combination give desired weak electrolyte. Lambda infinity of weak electrolyte is calculated by addition and subtraction of strong electrolyte. For example, to determine lambda infinity of weak electrolyte, just say for acetic acid, 3 strong electrolytes, that is sodium acetate, NaCl and HCl, are selected. Their lambda infinity values are predetermined. So from Kohlrausch law, one can write lambda infinity for sodium acetate is equal to lambda for acetic acid ion plus lambda Na plus. So lambda CH3COO minus plus lambda Na plus. Lambda infinity for HCl, it is always equal to, according to Kohlrausch law, lambda H plus lambda Cl minus. Lambda infinity for NaCl, it is equal to lambda Na plus lambda Cl minus. So what happen if we add equation number 1 plus 2 and subtract equation number 3 from them? So lambda infinity for sodium acetate plus lambda infinity of HCl minus lambda NaCl. So we comes like this, that is lambda CH3COO minus plus lambda H, because in this case lambda Na plus is cancelled by this positive lambda Na plus value. Lambda Cl minus is cancelled by this, and according to Kohlrausch law, it is nothing but lambda infinity value of your acetic acid. Second application of Kohlrausch law is determination of degree of dissociation of weak electrolyte. Weak electrolyte do not ionize completely. The fraction of total number of mole dissociated at any concentration is called as degree of dissociation at that concentration. It is generally denoted by alpha. So alpha is equal to number of moles dissociated divided by total number of moles. Equivalence conductance at any concentration, that is lambda C, is directly proportional to moles dissociated, while lambda infinity is equal to lambda cation plus lambda anion is proportional to the total number of moles. So alpha is equal to, that is degree of dissociation, is equal to lambda c divided by lambda infinity. The value of lambda c can be determined experimentally, it is important, and lambda infinity can be calculated using Kohlrausch law. Hence one can calculate degree of dissociation. Third application is determination of solubility of sparingly soluble salt. First, what is meant by sparingly soluble salt? Certain salt saturate solution at very low concentration called as sparingly soluble salts. The concentration of solution is so small that it can be considered as infinite dilution. Since the solution is saturated, this can be taken as solubility of salt, that is S. According to definition of equivalence conductance, lambda is equal to K divided by C, where K is specific conductance, C is concentration equivalents per meter cube. So lambda infinity is equal to K by C. So C is equal to K divided by lambda infinity. But as the solution is saturated, concentration is equal to solubility, that is C can equal to S. So S is equal to K divided by lambda infinity or K divided by lambda positive plus lambda negative. KSP, that is solubility product, is related to solubility. KSP is equal to S square for univalent electrolyte, that is AB type, for example barium sulfate. KSP is equal to 4S cube for unibivalent electrolyte, just like AB2 type. Next application of Kohlrausch law is determination of ionic product of water. Generally, this application is asked in the examination. Ionic product of water is defined as the product of ionic concentration of H plus and OH minus ion in pure water, and it is given by Kw is equal to H plus concentration of H plus multiplied by concentration of OH minus. According to Kohlrausch law, we can write lambda infinity for water is equal to lambda H plus plus lambda OH minus. So its value is this lambda H plus value and lambda OH minus value. It is 349.8 plus 198.5. After addition of this two value, we comes with 548.3 per ohm centimeter square. We know that equivalence conductance is equal to specific conductance multiplied by volume of water containing 1 gram equivalent of ions. So volume of water containing 1 gram equivalent ion is equal to equivalence conductance divided by specific conductance. After solving this, we got 98.97 multiplied by 10 raised to the power 8 per 8 centimeter cube. Therefore, 1 centimeter cube water contains 1 divided by this quantity, which is equal to 1.01 10 raised to the power minus 10 gram equivalent. So concentration of H plus or OH minus ion is equal to 1.01 into 10 raised to the power minus 10 gram equivalent per centimeter cube. Just convert this centimeter cube into liter. So that is equal to 1.01 multiplied by 10 raised to the power minus 7 mole per liter. But the number of both ions are equal in water at room temperature. So Kw is equal to concentration of H plus multiplied by concentration of OH minus. So this is the value of H plus as well as OH minus concentration. So multiply these two values, we comes it 1.02 10 raised to the power minus 14. So in our next class, we are going to see some numerical on Kohlrausch law. Thank you very much.